Hello, can you hear me?
Yes, I can hear you.
So, as I put in the chat box, Professor Hayashi is now going to hospital with some injury in the little finger of the book. And so today he will be absent, so and I will do some chairperson in total. And the first speaker is, sorry. In the chairperson of the first talk is Moriyoshi Sensei, I think.
Yeah.
All right.
Moriyoshi, hi.
Hi. Dewa. Okay, the first speaker is the Professor Song from Nagoya. Do you hear me?
Yes, I can hear you.
Okay,
Do you hear
okay.
me? Okay, yes.
Yes, the first speaker today is the Professor Song from Nagoya University, who speaks about quantum private information retrieval. So please start.
Yeah. Thank you for the introduction. I'm Seungwan Song from Nagoya University. Today's talk, I'll explain the quantum private information retrieval. So this private information retrieval is a cryptographic protocol, and so I consider the quantum version of this problem. So basically, I mainly in the first half of the talk, I'll explain our result on the quantum private information retrieval capacity. So I consider this capacity is the information theoretically optimal efficiency of this cryptographic protocol. So at first, I summarized my research results on this topic. And in the second half, I'll focus on the concept, a construction of a QPR protocol with colluding servers, very specific case. And in this construction, we encounter a symplectic matrix over finite field with certain linearity condition. So I mainly discuss about this, the existence and the minimum field size of this symplectic matrix in the second half. And this talk is based on these 4 publications. So this is the first 3 publications is yes, first 3 publications is with a joint work with Masahito Hayashi, Professor Hayashi, and the last one is with Alex Holzbauer, Pla, and Hayashi and Holanti. So, and it is on the archive. I heard that I will upload. Alex will upload this paper on the archive today, so it will be available within a few days. So let me start from the private information, our result part. So before we go to the quantum world, I want to explain what is this private information retrieval problem. So I call it PIR in short. A PIR is a retrieval protocol without revealing which message is requested. And it is first studied by Chor et al. In 1995. And this protocol is easily understood by comparing with this retrieval without secrecy scenario. So like in the left figure, let's say that a server contains F messages, F files, M1 to MF, and a user wants to retrieve one of these files, MK. So K file is the user's targeted file. In that case, the user sends K and receives MK, so the user knows what is MK. So this is simple, but in this case, the user's information of K is leaked to the server. So this protocol only requires the correctness of the retrieval. On the other hand, in the PIR we want to keep this K secret from the server. So we have one more condition that users called user secrecy. The user secrecy is means that the server doesn't know what is the K. So for this, the user sends some query Q instead of the K and receives the answer, and the user recovers MK, but the server shouldn't know what is the K. So when we consider these user's request K and the query as a random variable, this user secrecy is defined as the independence of these two random variables. So at first glance, it seems quite tricky to make this PIR protocol, but there is a very simple solution of just downloading all files. So if the user sends to the query that he wants to he wants to download all files, then downloading all files, then the user can pick the targeted file MK from the answers. But server doesn't know which one is exactly the targeted file. So it is possible to achieve this PIR protocol. So because it is possible, then our interest moves to how we can efficiently implement this protocol. As you may notice, this protocol is a very silly solution, because downloading all server, for example, downloading all Amazon server is quite impractical answer. However, it is proof that this trivial solution of downloading all is optimal. So for improving this communication efficiency, there have been mainly two approaches. The first approach is a PIR with computational assumption. So yeah, there are many studies. So by using this computational assumption, we can relieve this user secrecy condition. We can relieve this secrecy condition, a little bit weaker condition. So that is one approach. And the other approach is PIR with multiple non-communicating servers. And in this talk, I mainly talk about this second approach. So let me explain more about this multiple non-communicating server PIR. So in this picture, we illustrated the two server PIR. So in this setting, we consider that all of the files are copied to each server. And most importantly, we assume that the servers do not communicate with each other. And this no communication condition is very important for better solution. So with this multiple server setting, the user sends each of the queries, different queries to each server, and receives the answer. And from these answers, the user recovers the targeted message MK. And because the servers can't communicate, the secrecy condition is changed as K is independent of Q1 and K is also independent of Q2. Then each of the servers cannot get any information of the K. And usually, these multiple server protocols, most of the known protocols are one-round protocols. And to give you how it improves the efficiency of the protocol, how this setting improves the efficiency, I want to give an example, toy example given by the Chor et al. In the first paper of the PIR. So in this example, we consider there are 5 files, M1 to M5, and which is just 1 bit in here. And the user wants to retrieve the 5th file, k equals 5. So M5 is the targeted file. In that case, the user chooses sends these queries. These queries are constructed as just Q1 is just a random subset of the indexes 1 to 5. So for example, the Q1 is chosen as 1 and 2 and 5. And Q2 is defined as exactly the same as the Q1, except for the position of K. So it is 1 and 2. So, and then the server returns the answers, the sum of the files indexed with the queries. And the user subtracts these two, then the user knows what is this targeted message M5. So, and this protocol is a PIR protocol because Q1 was just a random subset so it is independent of K. And Q2 alone is also a random subset, so server 2 also doesn't have any information of 5K here. So this is a PIR protocol. And in this protocol, the user only downloads 2 bits from the servers. And even if the number of files grows really large, if even in that case, the user only downloads 2 bits, it's enough. But when we consider the solution of downloading all files in the server, then the cost will increase very large. So this protocol is very inefficient, very efficient solution compared to just downloading all solution. So the next question we have is how we can improve how much we can improve this efficiency when we consider in the multiple server settings. So this problem is solved by Sun and Jafar, and they consider the notion of PIR capacity. So in their setting, they considered there are n servers and f files, and the size of each file is m, equally sized as m. And in that case, they evaluated the efficiency of the protocol as a PIR rate, which is the number of retrieved bits per 1 bit download. So this rate is equivalently defined as the size of MK, the download file MK, over the total download size. So total of the sum of these downloaded bits. And from its definition, this rate is upper bounded 1. And because the rate of downloading all is 1 over f, because there are f files, so downloading all, by downloading all, we only have 1 file it's retrieved. So downloading all has a rate of 1 over f. So for good PIR protocol, we expect that the rate is between this 1 over f and 1. And so we want to increase this rate as much as possible. So the PIR capacity is considered, and this PIR capacity is defined as supremum of this rate when the number of servers and number of files are fixed, but the size of files m is arbitrary. So in that case, the supremum is considered defined as a capacity, and it is proved to be this value. Here we consider the n and f are fixed, but m is arbitrary. But this is a quite natural condition because we usually use megabyte files and gigabyte files, and that's a really large. That's really large size compared to the number of files and number of servers and number of files. So Sun and Jafar derived that the capacity is this value. This value looks a little bit complicated, but as the number of servers goes to infinity and goes to infinity, this value approaches to 1, which is the trivial upper bound of the PIR rate. So it means that as we increase the number of servers, we can achieve better. We can achieve a quite optimal capacity, optimal rate, which looks really efficient. So I move now to the quantum version of the PIR. So I call it QPIR. The problem is just the same, except that the users and servers communicate with quantum communication. Interestingly, there is an efficient QPIR protocol. Here, efficient means that equals to less than the downloading all is better than the downloading all solution, even with the 1 server case. So it is proved by Legal and Carantis et al. Oh, sorry. But unfortunately, if we consider a little bit stronger server model, which is called the species server model, then it is proved that downloading all is optimal, and it is optimal even with we assume the prior entanglement between the user and the server. And in our work, we consider the multi-server case, multi-server quantum PIR, and we derive the quantum PIR capacity. And the communication model we've considered is like this figure. So here, the green ones are classical information and magenta are quantum. So again, we consider the files are classical. And we assume that the servers had some prior entanglement for making the quantum advantage. We assume this prior entanglement. And the user wants to retrieve this for classical file MK, and for that, the user sends the classical queries, not the quantum queries, and downloads the quantum answers. And at the end, the user applies the quantum measurement on the received state to retrieve this MK. So we consider in this model, and we define the QPIR rate in the same way as the classical PIR rate. The only difference is that it is defined as a retrieved bits per 1 qubit download. It is changed as from bit to qubit. And as in the classical case, this rate is expected to be in between this 1/f and 1. And the capacity is defined as a supremum, and we derive that this capacity is exactly equal to 1. So this trivial upper bound of the rate is achieved with quantum setting. One interesting thing is that even with the, we only require that this n is greater than or equal to 2. So only with the 2 servers we can achieve this capacity. So it is, in the classical case, we need to increase the number of servers to get the better capacity, but in quantum case, 2 servers are enough. And we also considered and derived the quantum PIR capacity in several other settings. So I introduced several variants of the PIR and QPIR. The first variant is called the symmetric PIR. In the previous PIR, we only require the correctness and the user secrecy conditions. And in here, we also consider the condition called the server secrecy. It means that the user only obtains MK, but no other information. So for example, in the downloading all solution, the user downloads all of the files in the server. So that is not symmetric because the user also obtains other files in the server. So this is the first variant. And the other variants of the QPIR is a T-private QPIR. So in this case, we consider the case that at most 2 T servers communicate to know what is the K. The important assumption in the multi-server PIR was no communication between the servers. But this assumption of no communication is quite restrictive assumption. So we want to relieve this assumption a little bit more practically. So we consider the T-private QPIR. So in here, the user secrecy is changed as user T secrecy, which means K is secret to any T servers. And furthermore, we also consider the QPIR with distributed storage system. So in here, the correctness condition and user secrecy condition is the same as the original QPIR problem, but the change is that the servers contain some different files. It means that instead of having, in the previous case, all servers contained a copy of the same files, but in here, we encode the F files as n parts and distributes these n parts to each service. This setting is considered to be practical because it can reduce the cost of saving all of these files. Because yes, the copying is a very inefficient way of saving all the files. So this distributed coding system is used for the storage's efficiency, and it is also considered for it is sometimes considered for the reliability against the some malicious actions of several servers. So in any case, this setting is also considered in our paper. So in this table, I summarized the classical PIR capacity and the quantum PIR capacity. So these are our results, and these are known classical counterparts. So we have considered in many settings. The first one is just the PIR and the symmetric PIR, and the multi-round PIR and the symmetric multi-round PIR. So these in all of these cases, we proved that the quantum capacity is exactly equal to 1. And we also proved the T-private case, and even in the T-private case, the quantum capacity is still 1 as far as the number of colluding servers is less than the half of the servers, but it also it decreases a little bit. And when there is a coded distributed system, then it is generalized. The T-private case is generalized to this case. Yes, this is the first half of my talk. Yeah, thank you very much.
Thank you.
Yes.
So the questions or comments from the audience? I have one. I'm not specialist in this area, but this table explains it very well. And I wonder in the first 4 cases, the quantum capacity is all 1. So what is the kind of the reason, or do you have some the easy explanation of that property?
Yeah. So indeed, very simple. Indeed, in the quantum case, very simple protocol achieves this capacity 1. So that's basically the reason that we can achieve this capacity. And the reason that we can construct this very efficient, simple protocol is we can use just as the property of the quantum entanglement. So in the quantum information theory, there is a well-known fact that if by transmitting 1 qubit, we can send the 2 bits. By presenting 1 qubit, we can convey 2 bits. So that is called the super dense coding in the quantum information theory. And it is very similar. Our protocol is very similar to that protocol. So if we twice these capacities, we almost achieve this 1, because I mean that twice of this symmetric, for example, twice of this symmetric PIR is greater than 1 usually, but from definition, it can't exceed the rate 1. So it becomes so yeah, it becomes 1. Yes.
I see. So quantum capacity is in some sense the insensitive for the protocols. You mean? In some sense.
Yeah, in some sense, yeah, it is really it is directly related to the very simple protocols in the quantum information theory. Yeah.
Then what is the difference to the last 4 cases? There we have the non-trivial quantum capacity. Well,
Yeah,
what is
so,
the key property? Yeah.
Yeah, here, yeah. So in this case, we have two cases. We still have a very good solution, good result of capacity one for half when t is less than half and this value is less than half of n. The problem is that if this case and this case, we can't fully use the power of the entanglement. So maybe I can put it another way, that for this case, we can say that we can prove from the secrecy condition, we prove that we can fully use the entanglement. We can fully use the entanglement for transmitting, for achieving this capacity one. But when there are more servers, for example, when here T means the number of colluding servers. So when more than half of servers collude, then it is more restrictive condition. By this restrictive condition, it becomes more like, so it becomes very difficult to fully use the quantum entanglement. So that's the reason, basically.
Oh, all right, yeah. The entanglement, the kind of the word I heard, but I do not know the exact kind of the notion. Anyway,
yeah.
So the Professor Hayashi is back now. So you have question or comments now, or from other people, questions or comments?
Hey, I have a question. Could you go back to the slide that has examples for two server PIR?
Here?
Yes. So you say that the query is independent of target index k, but in this example, you must include the target index in Q1, right?
Oh, no. Actually, it is not. So it's okay that the Q1 and Q2 are inversed, and then in that case, the user knows where the 5 is included. So the user can, in that case, for example, Q1 is 1 and 2, and Q2 is 1, 2, and 5. In that case, the user just subtracts A2 from A1.
Yeah, but Q1 and Q2 must include 5, right?
Yes, one of the Q1 and Q2 should include the 5. So, but the important, so here because we assume that the servers do not communicate, so we can consider K is each of Q1 and Q2 are independent of K. We can say that. But of course, if we collect the Q1 and Q2, then it is, of course, it dependent on this K.
All right, and yeah, it's just a bit. Yeah, makes sense.
Yeah.
Thank you.
Thank you.
Okay. So other questions or comments? If not, so yes, please resume your talk, Professor Sun, please.
Yeah, thank you. So I move to the second part. In the second part, I only focus on this result, this red part, the T private PIR. I will consider about the protocol construction that achieves this capacity. So our capacity was defined as the supremum of the PIR rate. And we prove this capacity by two parts. The first part is the achievability part, and the second part is the converse part. So in the achievability part, we construct the capacity achieving protocol. And in the converse part, we prove the tight upper bound of the QPR capacity with entropic inequalities. So basically, this converse part proves this protocol is optimal. And in the remainder of this talk, I only consider about this capacity achieving protocol. And our capacity achieving protocol is obtained by this theorem. So this theorem states that when there exists a matrix A with some two conditions, then there exists a symmetric T-private PPR protocol which achieves the PPR capacity. So basically, if we have this matrix with these two conditions, we can achieve our achievability part is proved. So the problem of achievability reduces to finding this matrix with these two conditions. The first condition is just a simple, the symplectic condition. So A should be symplectic matrix. So this is defined as this inequality. So A should satisfy this this equation. And the second condition is defined with this A prime, another which is a submatrix of this matrix A. So A prime is defined from 2t columns of this matrix. So it is a 2n times 2t matrix. Oh, sorry. So A was the 2n times 2n matrix over finite field FQ, which is a finite field of order Q. And so because it is a submatrix of 2t columns, it is a 2n times 2t matrix. And we denote the rows of this matrix as R1 to R2n. In that case, the second condition is written as like this. So for any permutation of the n elements, the 2t rows are pi 1 to r pi t and r pi 1 plus n to r pi t plus n. These two 2t rows are linearly independent. So this second condition is a bit complicated, but it is basically the linear independence condition for any permutation, for any pattern. So with symplectic condition and linear independence condition, we need to find this A 2n times 2n matrix. If we find this matrix, then in the proof of our theorem 1, we concretely connect these two linear algebraic conditions to the secrecy and the correctness condition of the QPR protocol. So instead of explaining how we can prove this theorem 1, I want to focus on how the existence and the minimum field size of the matrix A in here. So indeed, if there is whatever the size of the field Q, if there exists A, we can achieve this. We can prove this achievability part. But in practice, if we construct our quantum QPR protocol in experiment, for example, then the small size of Q is better to be easily implemented. So we want to reduce the size of the field as small as possible. So these two are main interest in the second part of my talk. And before looking at these two conditions, I want to introduce the classical version of this theorem 1. There is a very similar theorem as this proposition 1 for the classical PIR case. So here, suppose that there exists a matrix B, n times n matrix B, which is invertible, and when B prime is defined as the first t columns of this matrix B, then any t rows of B prime are linearly independent. So if this B satisfies these two conditions, then there exists a classical PIR protocol that achieves the classical capacity. So this is very similar, but these two, the existence of this matrix B is much easier question than our theorem 1. This is because we can separate these two conditions. Please note that if we find that B prime satisfying the second condition, then we can trivially extend this B prime to satisfy 1. So because please looking at the condition, so because it is a linear independence condition of the rows, then we can say that these T columns are also linearly independent. And then yes, it's trivial to extend this B prime to by adding several appropriate columns, so we can make this B prime this B as an invertible matrix. So what we for the proof of the existence of this B, what is essentially is just proving this finding this B prime with this second condition. And there are many methods to find the B prime with second condition. It's relatively easy problem. So for one most naive solution is just choosing all elements B prime randomly. So by choosing all elements randomly, we can satisfy this second property, linear independence property, with high probability when the size of the field is sufficiently large. So it is a rather rare case that the randomly chosen matrix has linearly dependent rows. So by this method, we can prove the existence of the matrix B prime. However, this method only gives the existence of the method. So it just gives it just proves the existence with probability. So we usually want to find the concrete structure. So one very simple example is a van der Monde type matrix like this B prime. So in here, the alpha 1 to alpha t are chosen as distinct elements of the finite field. And then this matrix satisfies any t rows of these matrix are linearly independent. So this is this is from the well-known property of the van der Monde matrix. And more of these kind of structures have been studied in the Algebraic Coding Theory Society. So in the coding theory, the image of B prime is called the maximum distance separable code. And here the distance in the sense of the coding theory, the distance means the some error correctability, which is a good property for linear codes. So this maximum, this is because this MDS code has a maximum distance. This is the main interest of the coding theory, and there are many structures that achieves this property too. So with the help of the coding theory, we can find the solution of this B prime. So basically, we separate for the proof of the existence of B, we separated these two conditions, and we only considered this second condition. But in our theorem 1, we can't do that approach in here. Because yes, this seemingly complicated second condition is also about the linear independence. So by choosing all elements of A prime randomly, we can also say that the matrix satisfying this second condition exists with high probability. However, it's impossible. Generally, it's impossible to extend this A prime to satisfy this first condition of symplectic property. So differently from the previous classical case, we can't use the random method to show the existence of this matrix A. Instead, we concretely constructed the matrix A satisfying these two conditions. So the proof ID is by these three steps. The first, for symmetry n times n symmetric matrices X and Y, these two matrices are symplectic matrix. You can check these two are symplectic matrix by putting these in here. So with the symmetric property, we can have these two matrices satisfies the symplectic conditions. And the second thing we notice in here is that secondly, we said this x and y like this equation. So these are symmetric matrices. We define it. And the alphas is defined in this, alphas needed for the definition of x and y are defined from this relation. Here, the FQ, the finite field FQ is chosen to be the minimum extension field, minimum extension field of the prime field FP, which contains alpha 1 to alpha n plus 2t minus 2. So FQ is defined like this, and this alpha satisfies this relation. So this relation means that alpha I is not included in the extension field in the middle. So by adding alpha I to this extension field, we can it strictly extends the finite field by adding this alpha I to here. So this FQ is constructed by gradually extending the prime field. So these alphas are defined like this. And then with these two matrices, these matrices are symplectic matrix, and the multiplication of these two matrices are again the symplectic matrix. So this is A. So this resultant this multiplied matrix also satisfies the symplectic property 1. And it is not trivial that this matrix also satisfies the second condition, but we prove in our paper with just a linear algebraic argument. So the point in the main idea for proving this second condition, proving that this matrix satisfies the second condition, is that by choosing alpha like this property, we can say that x and y are invertible matrices, and with that property, we can prove that this matrix also satisfies the second condition. So this is the main proof idea for our theorem 2, the existence of the matrix A. So with this theorem, we prove that the achievability of our QPIR capacity. However, as I mentioned earlier, we want to reduce the size of the field. Here, this field size is exceptionally large. It's a doubly exponential to n and t here. So we want to reduce the size of the field, size of the Q here. And instead of directly considering optimizing the size of the Q, we proved this theorem 3 in here. So we connected our matrix A with the quantum MDS code. So we prove for this case, we prove that the existence of the matrix is equivalent to the quantum MDS code. So I'll explain the definition later, but for the quantum MDS code, there is a well-believed conjecture that called the quantum MDS conjecture that this quantum MDS code satisfy this inequality. So from this inequality, the size of the field Q can be roughly reduced as square root of n. So in the previous slide, our size was doubly exponential, but by connecting our notion with the quantum MDS code, we can reduce it roughly as the square root of n, and it is believed to be optimal. And even more, there are several studies that the equality of this lower bound is achieved. So I listed 3 studies, but there are many more studies about achieving this inequality. So by using this result, we can also achieve we can make this matrix A with really small field size. So here, here this quantum MDS code is defined like this here. So this matrix was just a linear algebraic notion, and the quantum MDS code is often defined with the quantum systems and the group property unitary representation, but it can also equivalently defined with the linear algebraic notion. So in here, we give the linear algebraic definition of the quantum code. So it is the NKQ quantum code is a subspace of a 2n dimensional vector space over a finite field, such that which is self-orthogonal and has dimension of n minus k. So here, the self-orthogonality is with respect to the symplectic bilinear form, but by this way, quantum code is defined. And any quantum code satisfies this quantum singleton bound, which is this equation 2. So here, another notion called the distance is defined, and this distance is the minimum size of the this WTV for all V in here. And this WT is the number of non-zero pairs in a vector. So this D is defined as a minimum number of non-zero pairs in this quantum code V, and this D is defined from this code, and this D is always satisfies this inequality. And the quantum MDS code is defined as the code which satisfies this inequality with equality to achieve the maximum distance. So the quantum MDS code is also a differently defined linear algebraic notion. So we connect our condition and this quantum MDS code definition. So this is how we consider the minimum field size of the matrix. And before finishing my talk, I want to discuss about this quantum MDS conjecture. Indeed, this MDS conjecture. This quantum MDS conjecture is indeed just a simple corollary of the MDS conjecture, which has been suggested in Segre in 1955, if more than 60 years ago. But it is simple. This conjecture is simply written like this, but it is not yet completely solved. So MDS conjecture is written like this. So let B prime be the n times t matrix over a finite field, such that any t rows are linearly independent. This is the matrix that we considered in the previous classical version of our theorem. And then this, if this B prime satisfies this arbitrarily independence condition, then the size of Q is believed to be lower bounded by this value. And this conjecture is only proved for the prime field yet. And it is also proved for the case that K is less than 2p minus 2. And these two improvements are quite recent ones. So, and this problem is not yet solved. So here's the conclusion. So in the first part, I explained that I summarized my result in this table. So we proved the quantum capacity, and these quantum capacities are greater than the classical capacity. And in the second part, I consider the construction of the T-private QPR protocol, which achieves the capacity, this capacity. And in there, what is important is to finding the symplectic matrix over a finite field with some linear independence condition. And we also consider the existence and the minimum field size of this matrix. Thank you very much.
Thank you very much for your talk. So questions or comments? Yes, please. Yanagida-san, please. Oh, this is yeah. Okay.
Sorry.
Questions?
Yeah, sorry, I have no question. But yeah,
Oh, all right. Yeah,
just
I
a
just
comment.
mistook since this icon is looks
Yes,
like
yes,
the
yes.
kind of raising hand.
But
So,
just
sorry,
one
it was
comment. Yeah,
the
just one comment.
the frozen.
Yeah, that's a very nice talk.
Yeah.
Very thank you.
Yes, indeed, indeed. Yeah, thank you very much for the very wonderful talk. So, questions or comments?
Okay, so you just have one question. Is it okay?
Yeah.
Sure, please.
Yes, so just in your work, you consider that the files are classical files or quantum files?
Oh, is it classical files in here?
Classical files, right?
Yes, in this talk, yes.
And what happens if the files are quantum, for example, with no entanglement between the files?
When
Do
the
you
file,
know what the quantum PIR capacity will become? Or is it open?
but you mean that for the case that the files are quantum files?
Yes, the files are quantum, yes. The quantum information, but there
Yes.
is no entanglement between the files.
Oh, in that case, yeah. Okay. In another work, not introduced today, we consider the quantum PIR,
Mhm.
and yeah. So I don't know. Sorry, I haven't considered seriously. Maybe.
Yeah, because
Yeah.
when you say that the rate is 1, you said that it is because you use super dense coding.
Yeah.
Super dense coding works for sending classical information, but not quantum information.
Yes, that's true.
So this probably won't work.
Yes, I think so. And the problem may be much complicated. I think.
Yeah. It's maybe worth considering at some point.
Yeah. Thank you.
Okay, thank you.
Yeah, thank you.
Other questions or comments?
Hi, this is Oscar.
Sure.
Hi, yeah, going a little bit on a tangent, but have people looked at doing these kind of things beyond quantum theory, like PR boxes, this kind of thing? Like, could you do better if you had if you relaxed some of the conditions of quantum theory, like if you relaxed the uncertainty principle?
Oh, as far as I know, there is no study for relieving these conditions. Yeah.
Okay, that could be interesting too.
Yeah, of course. And there's really not many studies for this problem, indeed. Maybe 10 or a little bit more than 10 studies for this PIR problem, quantum version of PIR problem. So there was no study for extended case, for example, in the general probability theory.
Okay.
Yep.
Questions or comments? Okay. Then let's thank the speaker again for the wonderful talk. All right, so we have 5-minute break and the next session starts exactly at noon, right? Okay.
Is it at noon in Japanese time, right? So is it it's 11 o'clock Chinese time, right? In 5 minutes, yeah.
Yes, that's true.
That's Japanese time. Thank you very much. Yeah, China, that's the 11 o'clock. Yeah, right.
Okay. See you then.
Ciao, I think they called me from the clinic. Is it possible? I was in the seminar. I couldn't answer. 10 minutes ago.
Professor Buscemi, is your mic is on, I think. Yes, okay. So it's time. So it's 12 o'clock in Japan and 11 o'clock in China. So let's start the next talk. So next talk is by Professor Oscar Dahlsten. And the title of this talk is Universal Bound on Energy Cost on Bit Reset in Finite Time. So let's start the talk.
Thank you. Hi, everybody. So my name is Oscar Dahlsten, and I'm going to talk about this universal bound on energy cost of bit reset in finite time. I will explain in a moment what this means. These are sort of images of how you can do a bit reset by changing the potential of the system. This is joint work with Yi Zheng, who I think has visited Professor Buscemi and others in Nagoya. And he was a postdoc in my group until recently. And with Dario Egloff, who has recently done a postdoc in the Max Planck Institute in this place. And Kavan Modi, who is in Australia in this place, and he's also a visiting professor in SUSTech. And Yi Zheng is now in this place, affiliated with USTC. So just very quickly to say this, what SUSTech is. So the aim is something like becoming a leading international research university that is analogous to Stanford, because Shenzhen is sometimes called China's Silicon Valley. So a common stated aim for SUSTech is to be analogous to Stanford. And there is one of the world's largest quantum efforts that has very recently been created here, called the Shenzhen Institute for Quantum Science and Engineering. Apart from the things that I will talk about today, I also work on foundations of quantum theory, such as what we just mentioned in the last meeting, generalized probabilistic theories, quantum machine learning, and information thermodynamics, which is what I will talk about in this talk. But apart from this talk, I can mention that I also did several things on what's called single shot thermodynamics, which is when you make statements that are true for every single shot of an experiment. Like if you say, oh, the worst case work is this, then it's a statement that's true for every single shot of an experiment, as opposed to saying, if you say the average work is this. And I've done several things also on Maxwell's daemon. So first of all, explaining the title. So a bit, which is something like 0, 1, being reset, it means it's set to a fixed value, such as 0, independently of the initial value. A bit reset in a physical system, which is connected to a finite temperature heat reservoir, has a non-trivial energy cost. So that's the word energy cost. So for example, if you see this picture here, which is like Landauer's original picture, you would have a potential, a double well, like a bistable potential, and then you would squeeze, change the energies of this right well. And this means that you're actually, if the system is in the right well, you're actually adding energy to it, so it costs you work. And the subtlety is that in real scenarios, this reset is not done very slowly, but in finite time. It's not done infinitely slowly in particular. And this leads to a higher cost than the cost that you would have if you did it very, very slowly. So that's why we have finite time in the title. By universal, we mean that basically it has minimal assumptions, so that we try to assume as little as possible about what the potential is and what the time evolution of the system is, so that it can apply to as wide a set of hardwares as possible. So the motivation is, okay, so this there's a practical motivation and a foundational one. So the practical one is that bit reset, the heat dissipation from bit reset, it actually puts a limit on the speed of irreversible computers, as well as the energy efficiency, of course. So of course, this is if you spend a lot of energy on resetting bits, then you have lower energy efficiency in your computer, which is bad in itself. But maybe more subtly, it also limits the speed of the computer because the computer can only take so much heat, and this energy gets dissipated as heat. And for that case, so if you look, for example, at this graph here by somebody called Mike Frank, who has worked a lot on these kind of questions, like what is the future of computing and the fundamental limits on irreversible versus reversible computers. So he looks at the switching energy for transistors, which is what you do when you need to change the value of your node, whether it's at the high voltage or the low voltage, you would do this switch. And then you can effect a reset by doing that. And he extrapolates that we will reach the KT kind of regime around 2035, which is not that far away. But is this actually the real limit, the KT? Because in finite time, the cost is higher, and the KT log 2 cost is for the quasi-static case. So it may be that we start to really hit this limit even sooner. So there are many there are many papers on these things, including these ones that I mentioned here. And we learned recently that Professor Buscemi has also done something that looks interesting. And these are, so there are many impressive results, both theory, experiment, but they still contain some limitations. So they will assume certain settings. And that's why we think it's important to find a very general version of the Landauer limit. And actually, this whole thing kind of started by we went to a workshop and presented an earlier paper. This is a PRL with Cormac Brown, Andrew Garner, and me, and Vlatko Vedral. And we seem to have a different kind of time scaling of the penalty to other people who were presenting other systems at the same workshop. We wanted to understand how system dependent is this cost of the extra cost if you do it in finite time. Okay, and then there's another more foundational motivation, which is that information thermodynamics, that studies the role of information in thermodynamics. In information thermodynamics, Landauer's principle is very important, and you have heard this phrase, information is physical, which is usually said together with Landauer's principle. So if we want to extend information thermodynamics to finite time, starting with Landauer's principle seems reasonable. Okay, so here's the outline, and I think I can get through this. So I'll start with non-equilibrium thermodynamics, and then define bit reset. And then we will take, around that point, we will take the first break. Then we go to the main result, which is a bound on the work penalty. And we will justify that by a 3-step process. Step 1, step 2, step 3, that I will explain later. And then we will sort of discuss what do we learn from this, and then summarize an outlook. So we start with non-equilibrium thermodynamics. And in some ways, this is very basic, but of course, it's also very subtle. So do stop me at any time. So firstly, what are the states and the state evolution? So let's start with the simplest case where we have a discrete state space, and we just have probabilities. So if this were a quantum system, it would be diagonal in the energy eigenbasis. So we have the microstates of the physical system, and they can be labeled by some index I, which is 1, 2, up to some big N, and they have associated energies, EI. And you can generalize this to the continuous case in the normal way that you generalize sums going to integrals. But I don't want to write both notations. I will stick with the sums here. And then importantly, of course, each state has a probability P of t. So P1 of t all the way up to Pn of t, where t is the time. And a very key assumption is that when a system is in contact with a heat bath at temperature T, so if this green thing is your system, and then you have a heat bath, red thing here, then the P of T, these probabilities, they will undergo a stochastic, so like a random evolution towards a stable state, gamma, where the individual probabilities are these thermal probabilities, right? So e to the minus beta EI over Z. EI are the energies, beta is 1 over kT, and Z is the partition function, which is normalizes the distribution, so has this form. Now, the evolution of these probabilities is modeled by a Markovian master equation. So we assume the transition probabilities for the microstates do not depend on the past. And so these are the changes in the individual probabilities. And there's some transition rates, gamma ij, and you basically have some changes due to things going from state to j into I for each state to j. And then these gamma ij is the transition rates. And these are non-negative numbers, and they sum over the sum over j like this. So this matrix is 0, which follows from the fact that the sum of the probabilities is always 1. So the sum of the change of probabilities is always 0. And now we will make one significant assumption here, which is detailed balance. So we will assume that gamma ij, big gamma ij times little gamma j is equal to gamma ji times little gamma I. So this can be interpreted as saying that in a thermal equilibrium, if you're in a thermal state, so you see your probabilities of the gammas, then you have equal probability of jumping back and forth between these two states. So we have a kind of balance there. Okay, and this image depicts the between two levels, there is an associated transition probability, transition rate, gamma ij. Okay, what about heat and work? So we said that we had these microstates, and they have the energies and the probabilities. Now, we said that the P of T can vary due to the interaction with the heat bath from that master equation, but we will also assume, and this is basically a standard way of modeling things in stochastic thermodynamics. So we will also assume that the system Hamiltonian can change. And this is physically viewed as being an interaction with a battery system, or a work reservoir. So there's an external system now. So there's two external systems that are not modeled explicitly, but we only model their impact on the working medium system. So we call it working medium here because it's analogous to, say, a gas in the heat engine. Now, so we have the Hamiltonian depends on time because of the interaction with the battery. And this means that the energies depend on time. And then it follows that the internal energy change can be viewed as being composed of heat and work. So du can always be written as this, right? Because u is sum over pi/ei. So du can just always be split into two parts. But now, because we think of the probabilities as changing due to the interaction with the heat bath, and the energies as changing due to the interaction with the battery, then we call this contribution heat and this contribution work. So this is the infinitesimal heat, and dW is the infinitesimal work. So this is the standard kind of first law in stochastic thermodynamics. So now when we get into non-equilibrium cases, then this what happens to these things. So in particular, we define what's called the work penalty and the entropy production. So if we're very slow very slow driving, so very slow changing the Hamiltonian relative to the thermalization rate. This is called the quasi-static case. Then the system is approximately in the equilibrium state. So gamma is e to the minus beta h over z at all times. But in general, the system is chasing after gamma. So this is a picture of the state space that I find this a helpful way of visualizing what's happening. So these dots represent states at different times. So for example, the thermal state may undergo some evolution. That's this dotted line here, gamma of t. How can the thermal state change? Well, it changes because the Hamiltonian changes. So if the Hamiltonian changes, the thermal state will change and move up to here. Now, if you do quasi-static, then your state, so this blue line is your state. If you're quasi-static, your state will track the thermal state, and it will just do the same path. But if you're not quasi-static, it will be sort of falling behind and trying to catch up all the time. And they will not be exactly overlapping these lines. So that's what I mean by saying the system chases after gamma. Now, so we can define the work penalty and the entropy production in terms of how things differ from the quasi-static case. So the quasi-static work is the one where you have the probabilities are thermal. So remember from here, this part is called the work part. So we have sum over I, P, I, D, E, I. And that's for the infinitesimal work. So if you want the actual work, you need to integrate this over the path. And if you want the quasi-static one, you put the thermal probability in for PI. So that's what's happening here. So we integrate over from the initial to final time, and we sum over the energies, and we put in the thermal probability here. And this you can show is KT log of the initial partition function divided by the final partition function. And then you define the work penalty as the difference between the actual work and the quasi-static work over the whole path. Similarly, for entropy change, the entropy change is just the final minus the initial entropy, where the entropy is basically the same as the information entropy, except that we just use the natural logarithm and multiply by Boltzmann's constant. So it's really the same. The information theory entropy and the statistical mechanics entropies are kind of by definition the same thing here, up to these trivial differences. And the quasi-static entropy change is if you're in the state where you have the thermal state all the time, then you can prove that the quasi-static entropy change is Q of tau over T. So Q is the integrated heat. So I'm not including that proof now, but you can show that. And many of you have seen that, I think. And then we define the entropy production as the difference in the change of entropy that you actually have minus the quasi-static one. So that's the entropy production. So we have the work penalty and the entropy production. So the difference in the work and entropy respectively compared to the quasi-static case. Okay, so what about bit reset? So we're now going to model the bit reset process with non-equilibrium thermodynamics. A bit is associated with two logical states, 0 and 1. And the subtlety is that logical states may be associated with sets, omega 0 and omega 1, of underlying microstates. So the bit value probabilities are actually sums of microstate probabilities. So we have P0 bit. It's a sum over the probabilities of all the states that are associated with 0. And similarly for the bit value 1. So these states, omega 0 is the set of microstates that we would label as bit value 0. So for example, in this double well potential here, we might say that anything that's to the left of this middle line, any microstate which has a position to the left of that line is 0. And any microstate that has a position to the right of that line is 1. And then the probability of 0 is the sum over all of those, or the integral of all of those probabilities or probability densities. Okay, and then just a terminology thing is that we can call this PI the fine-grained probabilities and the big P bit as the coarse-grained probabilities. So it's like you're looking at it with a very fine precision, then you get the PIs. But if you have big chunks that you look at the state space in, then it's coarse grained. And then the definition of bit reset here, which is actually strangely often called erasure. So you have probably heard the word Landauer's erasure, but to me, erasure sounds like randomization a bit. So I avoid using that term. I call it reset. So the bit is reset up to error epsilon if it is set to 0, regardless of the initial state. So P0 bit of the final time tau is 1 minus epsilon. So the epsilon is the error in the probability that you may have the wrong bit value at the end. Okay, so how do you do bit reset in this model? So in particular, how can we increase P0 bit from the initial value of 1/2? Well, we said that we allow thermalizations, which change the microstate probabilities, the PIs, and we also allow changing the energies EI. And the basic idea is that you take the energies, make the energies in the set, in the microstates associated with omega 0, you make them lower relative to the energies in the set omega 1. So basically, the energies associated with bit 0 should be lower than the energies associated with bit 1, and then you thermalize, because when you thermalize, you're more likely to have low energy states than high energy states. So what you see here in this picture is that the energies of the set associated with 1 is going up, right? So time is on this axis here, and we have position on this axis, and we have a potential energy on this axis. So this is precisely doing that it's increasing the energies of the bit values 1. Similarly, in this case, we just have a 2-level kind of you can think of it as a spin, for example, system. And then we increase the energies of the let's say spin up, or whichever spin it is that we're calling 1. So this could be like a Zeeman splitting with an absolute shift. And then the probability of being a 1, if we thermalize at the same time, the probability of being a 1 will go down as we raise this level. So we will be more likely to be 0. But now this costs work because you're changing the energy of the system, and the system may be in this place. And then when you're changing the energy, that has to come from somewhere. And the thing that changes the energy is the battery. So Landauer's limit states, and you can calculate this, that if you take the case of epsilon goes to 0, so no error, then the quasi-static work is kT log 2. And you can't do better than that. And you can show that, for example, because you can prove that the entropy production is non-negative. And then you can use that to prove that. But I'm not showing you that explicitly now, but you probably know yourself ways of proving this. Okay, so that's the Landauer limit says that the minimum work cost is that quasi-static work, which is kT log 2. And now I will briefly mention the main result before doing an intermediate summary and then taking the first break. So the main result is that for any bit reset protocols within the framework described above, where you assume Markovian evolution and detailed balance, then the work penalty, so that was the extra cost on top of the quasi-static work, is lower bounded by 2 terms. So the first term is a relative entropy term, which is the relative entropy between the coarse grained distribution and the corresponding thermal final distribution. So this would be 0 if you did it quasi-statically, because then p bit tau would be equal to gamma bit tau. And the second term, here you see the error epsilon. So it depends on the error epsilon. And then this mu, I will explain more later, but it's a measure of how strong the thermalization is. So this will depend on your physical setup, like how quickly do you thermalize. And if you thermalize faster, then the penalty will be lower. And tau is the amount of time that you allow for the protocol. Okay, so here's the intermediate summary. We said that the system state is assumed to be in a thermal state if you do quasi-static protocols. So if you do really slow protocol, this is a thermal state. And then we define these two things. The work penalty is the actual work. So tau is the final time of the whole protocol. So this means the final, so t goes from 0 to tau. And the work penalty is the difference between the work, the actual work, and the quasi-static work. So it's the penalty for doing it in finite time. The entropy production is the difference in the end between the entropy change and the quasi-static entropy change, which I wrote as Q over T before. And we said that we can divide the state space into sets 0 and 1. And the bit reset with error epsilon means P1 is equal to epsilon. So here the P1 means the probability of bit value 1 at the end. And I said that we will argue that the work penalty is lower bounded by sum of two terms, the relative entropy term, and this other term that has the error and the strength of thermalization and the total time tau in it. Okay, that was the intermediate summary.
Yeah, thank you very much. So is there any question or comment? So I have one question. So I understood what is the task of the bit reset, but I couldn't connect its motivation with its task. So what is the motivation of this task? And
okay, yeah. So why do you want to do it in the first place?
Yeah.
So I guess that's a bit like this thing here. So when you do a computation, so there are different approaches, but the standard method of computation is called irreversible computing.
Yeah.
And then you have so in your computer you have all these little like conducting segments called nodes.
Yeah.
And they have some state, but often you want to set them to a certain state. So you want them to become equal to some other bit that you may have somewhere else. Or you want to even erase your memory to reset your memory so it's ready for whatever comes next.
Yeah.
So this operation happens a lot in the current types of computers that we have, that you have a node and then whatever value it's on, if it's at the high or the low voltage, you need to set it to the some fixed value. So that is a bit reset.
So basically, we need to reset the memory again and again and again. So for that purpose, a bit reset is necessary. Is it right?
Yes, and maybe it's a bit more than just resetting the memories, because you may want to set a bit to a fixed value.
Oh yeah. Okay.
Yeah.
Yeah. Thank you.
Yeah, no problem.
Is there any other question?
Can I ask a question?
Yeah, hi.
First of all, sorry, the audio started by itself and I disturbed your
Oh, this is
presentation.
Francesco. Okay, hi.
Oh, yes. Hi, Oscar. Nice to see you.
Okay.
I wanted to ask you something that is probably marginal for this introductory part, but what is exactly the role of detailed balance here? Why do you need detailed balance, or would you be able to get away without detailed balance condition?
Yeah, so some of the calculations use it. It basically simplifies some calculations. At the moment, we unfortunately need it. It is a common assumption, but it's not. You can create models that don't obey this assumption, but still kind of work as thermalization models. So it is a non-trivial assumption, and that's one of the things that would be great to get rid of. But at the moment, we haven't.
All right. Thank you very much.
Yeah, cool.
Is there any other comment or question? Okay, if there is no, so Professor Dawson, please keep
Yeah.
starting your talk.
Let's see. Where was the? Oh, this was the intermediate summary. Can I just ask how much time do I have left?
Sorry, you have 20 minutes now. Yeah.
Okay.
Yeah.
Yeah. So now I wanted to go through the main result and sort of outline the proof. So the main result was again this thing that the penalty has a lower bound for whatever process you're using, as long as you have this Markovian master equation and detailed balance. Then it's lower bounded by the sum of these two terms, the relative entropy term and this second term, which has the bit reset error in it, and the strength of thermalization and tau. So basically, the stronger your thermalization and the longer you allow for, the lower the work penalty. And same if you allow for a bigger error, you can have a lower work penalty. And the proof has 3 steps. So we quickly go through those. So for step 1 is to rewrite the work penalty in terms of relative entropy. And this step is actually not new, but I'm including it because I find it very illuminating to understand what's going on. Okay, recall that we define the work penalty as the difference between the actual work and the quasi-static work, and the entropy production as the difference between the change in entropy from the initial to final minus the quasi-static change in entropy, which is Q over T. So the first step is to note that this work penalty can be written in terms of 2 terms. And the terms are the change in relative entropy between the state and the thermal state. So this relative entropy between the state and the thermal state is a really key quantity in thermodynamics, and you can derive many things by focusing on this quantity. So the change in that. So initially they would be, for example, in this image, they would be 0. So initially they have this guy is often 0 here. And finally, you see there is some difference between the two. So P of tau is not the same as gamma of tau. So there's a buildup of this kind of thing over the, or there may be a buildup over the protocol. And the second term is this entropy production term, which is here. And we'll explain where this comes from in a moment. And of course, the relative entropy here is defined as this guy. So sum over I, pi log pi over gamma I. And so where does this come from? So this is the part that I find really nice to just see this. Why do we get 2 terms? So they can be understood from, and if you can call this in a fancy way, information geometry. And for example, Shiraishi has done, et al. Have done papers on this. Basically, if we think about this term, the relative entropy between P of T, the distribution of state, and the thermal state, this thing is this P of T is chasing after gamma T during the thermalization, and there will be some change in this guy. And we can break it into 2 parts because the relative entropy depends on the state and on the thermal state. We can break this into 1 part associated with the change in the state. So this is maybe a slightly complicated way of writing it, but this means P dot dP dP of gamma. So this is the normal way that you can split a derivative into the sum of partial derivatives. So this means the sum over Pi dot, and then the partial derivative with respect to the Pi's. That's what this term means. And this term is the corresponding thing for the thermal state. So if you keep the state of the system fixed, but you change the thermal state, then you have this contribution to the total change in D. So do stop me if anything is unclear here. But basically, this is where the 2 terms come from. Why do we have this equation with 3 things? because what we have is we have this change in relative entropy here. And this guy is equal to the sum of two terms, which is WP, the work penalty, and the entropy production. Because you can actually, by just going through the maths by brute force, you can see that this can be rewritten as D dot is equal to minus the entropy production plus the work penalty. So these terms, this first term becomes the minus of the entropy production, and the second term is the work penalty. And this kind of makes sense because the first term is associated with changing the entropy of the state, because it's associated with changing P. And the second term is associated with changing gamma, which means that you're changing the Hamiltonian. And that's where the entropy production is related to the change in entropy, and the work penalty is related to the work. So this is one way of seeing kind of geometrically, why do we get two terms? Okay. So now we have the two terms, and now the next step is to rewrite these in terms of the coarse-grained quantities. So coarse-grained the relative entropy and the entropy production. First, we coarse-grained the relative entropy. So we had the work penalty has two terms, the delta D and the sigma. So we're going to focus on the delta D term firstly. The system is initially in a thermal state here for these bit reset protocols. So we will assume now that the delta D is actually equal to just the final term. So the relative entropy between P of tau and gamma of tau. And we first show that this thing can be lower bounded by its coarse-grained counterpart. So the relative entropy of the fine-grained states, to the relative entropy between the fine-grained state and the fine-grained thermal state, is an upper bound to the relative entropy of the coarse-grained state and the coarse-grained thermal state. And these are the definitions of these states. So it's just that you sum over these sets to get the coarse-grained states. You can prove this using, as you know, often these kind of proofs use what's called Jensen's inequality, or there's a version called a log sum inequality. And I've put that in one of the final slides, and it's also in the paper. And similarly, and this is a longer, more complicated argument, the entropy production is an upper bound. The fine-grained entropy production can be shown to be an upper bound to the coarse-grained entropy production. And this part is a bit subtle, but I would just kind of highlight that it's subtle. The transition rates at the coarse-grained level, they actually depend on the underlying microstates. And this is what you would call hidden Markov dynamics, that there's an underlying Markov model, but what you're looking, the level that you're looking at will look non-Markovian. So we have in particular, we have these, the change in the bit probabilities have these transition rates, and they are actually, they will depend on what happened before. So you have to be a bit, we have to take care when we do these calculations. I should mention this equation as well, because this defines the mu that I mentioned before that appears in the main statement. So we can show that the coarse-grained master equation can be written as this, that P dot bit is equal to mu for some rate mu, and P bit T minus PST, which PST here means the stationary state of the coarse-grained dynamics. So the thing that map is, I mean, you can see that from this equation that there is a kind of, that if these guys are equal, then nothing happens. So this is a stationary state here for the given dynamics at that moment of time at the coarse-grained level, and that's this PST, ST for stationary. So this rate mu is saying how fast, how big is the change, P dot. So how fast are you, in a sense, thermalizing at the coarse-grained level? And maybe here I should just mention that this sigma dot bit or sigma bit is in principle experimentally accessible by measuring the transition rates at the bit level. And there are This is actually how several experimental papers evaluate these things. If you want to see what the work or the heat is that they actually track the trajectories of the particles, which is a method that works for classical systems. Okay, so now we can put these two things together because we had the two terms, the fine grain terms, and each of those we have bounded by the coarse grain terms. Now we can show the work penalty is upper bounded by the coarse grained relative entropy, the final relative entropy, and the coarse grained entropy production. And this is not tight in general, but it's tight in the case, a special case that people often study called local equilibrium. And in the local equilibrium, the probabilities of the microstates conditional on the bit value are thermal. But the bit value probabilities may not be thermal. And this is studied, for example, in these papers, this special case, because that case simplifies the mathematics. But we're not restricting to that case, but we're just pointing out that it's tight in that case. And this is a comment that we realized in the late stage. We have not fully explored this, that we think that this suggests that two-level systems can outperform mesoscopic systems, or systems with many microstates, in terms of the work penalty in general, because for any coarse-grained master equation, then you can find a two-level system, so like a qubit, such that the work penalty lower bound, this lower bound is saturated. And then I should also mention something you're probably wondering about is why don't we allow for quantum coherence? And this basically goes back to, I mean, there are many people who have made this observation before, but for us, it goes back to this paper, Brown et al., where we see that if you allow for coherence, you get worse performance in the bit reset. And basically, you will end up, when you measure in the energy eigenbases, you will end up generating entropy. But that's something that it may be that there's some other way that you can make coherence help. So that's another interesting question. Okay, so, and then finally, the entropy production to bound that. So this is using the speed limit approach, and it's in particular inspired by Shiraishi. So following, we sort of modified their argument so that it applies to our case, Shiraishi et al. So speed limits were first proposed to operationalize time-energy uncertainty relations, but now they're used for many things. And the basic idea is that you say, okay, the time needed for something is the distance divided by the speed. But distance and speed can now be interpreted as the state moving in the state space, like in this kind of picture. It doesn't have to be a particle with dx by dt speed. And so we prove the following speed limit using the method or modifying the method of Shiraishi et al. To the coarse-grained case, where so the time needed of the protocol is upper bounded by the distance. This is the one norm distance squared of the, we see here is the final bit state P of tau, and the initial bit state P of 0. So this dotted red line here is a depiction of that distance. So the time needed depends on that distance. But you need that distance to be non-trivial because you're resetting the state. Divided by these two things. So this is this mu averaged is the time averaged of the mu that I showed in the previous slide, which is the rate of thermalization at the coarse-grained level. And sigma bit is the coarse-grained entropy production that I mentioned before. And L is, as I said, the one norm distance defined by this equation. And so in the analogy of this, the time needed is distance over speed, is lower bounded by distance over speed because you could take a silly path. The speed in that, you see that the speed therefore is this mu times sigma bit of tau. Okay, so these three steps taken together give us the result. So The first step was to look at the relative entropy between P of T and gamma of T, and split it into two terms. And these could be rewritten as the entropy minus of the entropy production and the work penalty. And then you can rearrange and integrate to get that the work penalty is a sum of two terms, which is these two, the change in relative entropy and the entropy production. And then we coarse-grained, we showed that these guys are lower bounded by their coarse-grained versions. That was the second step. And then we showed that the coarse-grained entropy production has this lower bound from the speed limit. And that's where we get this general equation from here. So the work penalty is lower bounded by the coarse-grained final relative entropy between the state and the thermal state, plus this term. Okay, the relative entropy time scaling, you see this is a little bit frustrating that here we have this kind of closed form expression, and here we've written it as a relative entropy without stating how it scales with tau explicitly. So we think that this term will in general decay exponentially in tau, but at the moment we can only prove this for special cases. So for example, in this discrete level shifting protocol in a two-level system. So if you have a truly two-level system, then the coarse-grained and the fine-grained states coincide. And then you can show, because of the lack of free parameters, basically, that the thermalizing evolution must respect this evolution that's called a partial swap model, because it's equivalent to, with some probability, swapping your state with the thermal state. So P dot of T is mu of T times gamma of T minus P of T. So you see if gamma of T is equal to P of T, then nothing happens. And we often assume that mu of T is time independent, so it's equal to mu for simplicity. So that's a special case. Now, and this is also used as a simplified collisional model for thermalization more generally away from two-level systems. And it has been used to describe relaxation in NMR qubits. Now, so the idea is in this picture, we have the two levels, and initially they're both zero, and then we stepwise lift to the second level. The stepping is just something we introduced to make the calculations easier for us. So we shifted to up to some maximal energy Emax, and the increment, therefore, for each step is Emax over n, where n is the number of steps. And then you let the system thermalize for a time which is tau divided by n. So physically, this kind of thing, if you to implement it, you need the experimentalists to change the control fields much faster than the thermalization rate. And then in this case, we can prove that the relative entropy has an upper bound, which is exponentially in tau. So if you imagine big N is fixed, then you just change tau. So you change how long you thermalize in each step. And then you will see that this guy falls off exponentially. But we think this is true more generally, but in this case, we can show it. We can also do numerics in this case. This is the work penalty bound here. And we can test it to check how it looks compared to what you actually see exactly in this case. This does not, then when you want to check that, there's actually two cases. And this is a little bit confusing in the literature, that different papers may use different choices here. So you can choose to either lift your energy so at the end it would be at E1 of tau. And you can choose to make this a fixed value, or you can let it change depending on your reset errors. You could also alternatively fix your reset error. Therefore we have two images because these are two choices. So on this case, we have a fixed Emax, a fixed final energy. In this case, we have a fixed error. So the x-axis is tau. So how long do you spend doing this protocol? And on this axis is the work penalty on the y-axis. And we have different bounds and the exact values. So the exact is the black one, work penalty. And then the bound that we have up here is the dotted black line. And then you can see that it divides into two parts, the relative entropy part and the entropy production part. Basically, in both cases, you see that if you allow for longer time, the work penalty goes to 0. And you can sort of see that this red line is like an exponential decay. And what you will see actually, and we spent some time thinking about this, is that for short tau, then the relative entropy part dominates, and the work penalty therefore just decays exponentially. And for long times, the entropy production dominates, and the work penalty decays inversely linearly. So if you look at the literature, you will normally see this statement that the work penalty decays inversely linearly. I guess a key question here is for this part. So we need to basically look at, so we know it can happen, the exponential decay, but we need to look at whether it's important for real experiments where you do bit resets, for example, in computers. So the just another slide, similar slide on this, is that we had this work penalty here, and now we can also plot the boundaries between the regions where the relative entropy or the entropy production dominate. So we have in this case, we have the maximal energy Emax on this axis, the reset error here on the x-axis, you see there are different regions. And I think because of time, I will not go through it in detail, but basically when epsilon is large, then you can set Emax. So when the error is large, then you can set Emax such that the work penalty exhibits exponential scaling, which is region 1. When it's small, we seem to be stuck with the inverse linear scaling, which is region 2. Okay, and we encompass previous results in the following sense. So there is something called the overdamped Langevin dynamics, which is also called Brownian motion. And this is, it matches the original Landauer picture with a double well potential well. So people have used this to model such resets. And for example, including very recently this paper. And in the case where the reset error goes to 0, then this relative entropy term vanishes. And the penalty bound then becomes just this inverse tau scaling, consistent with this paper, recent PRL. But our bound also applies to two-level systems, such as the one that we did in 2014. And in particular, we don't assume any reset error value. We don't assume a specific landscape of the potential, and we don't assume overdamped Langevin equation. And this part is very interesting. And we've only really started with this, but so there's something called information throughput, which I will define on this slide. It's basically like how much computation can you do? So hardware accepts limited temperatures, and work applied for each reset is dissipated as heat, because that's where by energy conservation it has to go somewhere, and it goes into your computer. And so it would be the heating of the computer, and that actually puts a limit on the number of resets per time and space. You may be aware that the reason the computers are not running faster today is because of heat. So they made the choice to limit the clock frequency and keep miniaturizing the components. So you increase the number of transistors per square centimeter, but you're not significantly increasing the clock speed of the computers because of the heat. This is a paper by people from more that kind of community, and they use this terminology. So they say the device switching time is tau SW for switch. The number of binary switches per centimeter squared is little n. And then so these two things both mean kind of more computation if you have lower switching time and if you have higher n. So they define the information throughput as little n divided by tau SW. And you can define some energy cost of switching. That's the binary transition energy, E bit. And then the power dissipation would be P is equal to E bit times the B. And because we have a bound on E bit, we can bound the power. And I guess it's actually, there's not that much point for me to go through the details of what this bound looks like, because we have not analyzed it properly yet. So this is all very, very new. But that's one of the things that we want to do now, is to analyze this for different alternative candidate technologies for computation. Because, you know, there's talk about what's called beyond CMOS. Can we, what would be the next generation of hardware? And then the key question would be how well can it deal with this upcoming Landauer limit? And this is an image of showing how hot the computer is. It's a thermal image from this place. Okay, so to summarize, Landauer's principle implies that it costs at least kT log 2 of energy to reset a bit. And it's important for the limits of irreversible computers. And it's also of foundational interest for information thermodynamics. So how much was the work cost of a bit? So we show that for any bit reset protocols within this framework, assuming Markovian evolution at the fine-grained level and detailed balance, then the finite time penalty is lower bounded by some of these two terms. So it's a relative entropy between the coarse-grained bit state and the coarse-grained thermal state, plus the entropy production term, which can be lower bounded by the speed limit. So we had epsilon is the error of the bit reset. So if that's higher, you can have a lower work penalty. And if you have a stronger thermalization, then this mu will be higher. And that will lower your work penalty, as will increasing your tau, the time that you allow for the protocol. And I think that was, the outlook. So we should have really applied this to candidate technologies for irreversible computing and checking, for example, what these mu values are there and how much time they allow for each reset. And we want to probe whether it's really the case that quantum coherence cannot help, because maybe there is some clever trick that we can think of. I mean, we have done papers in the past as have others, on quantum Maxwell's daemons. And I don't at the moment see how that approach can help with this problem, but there could well be some clever trick that you can do with quantum things. Of course, one option is to use reversible, just treat it as a reversible computer, which is what Mike Frank wants, is that we should give up on irreversible computing and switch to reversible computers, which include quantum computers. That's certainly an interesting approach. And then, as Professor Buscemi already asked, can detailed balance assumption be removed? Maybe it should be possible, but we haven't done it yet. And a kind of standard question is, okay, with these statements for the average work, and can we make statements that are true for the single shot? So, for example, the worst case work, where it show that this bound is deterministically satisfied. Okay, so now I'm at the end, and thank you very, very much. It's the first time I give a talk about this paper like this. I hope it was understandable. Thank you.
Thank you very much. So, is there any question or comment?
It's again Francesco here.
Hi.
Can I ask you one more thing, always related with the, but first of all, thank you very much for the talk. It was very enjoyable and a good pace also. You didn't want to say too many things at once. So I really enjoyed your talk. Thank you very much.
Thank you.
I wanted to ask you something more about the detailed balance. It's something that also I've been thinking about. So could you say, like in few words, why you need that? Like, is there any place in your paper where you need to construct a reverse process, or where you need to derive some
yeah,
factorial relation, or
when the place that comes to mind is for the bound on the entropy production in terms of the coarse-grained entropy production, that we use a specific statement version of the entropy production which holds for detailed balance.
I see. I understand.
Yeah, but yeah, so this is but you, in principle, you can violate detailed balance. Like you can have, if you have a kind of cyclical flow that you maybe always jump from state 1 to 2, but never directly from state 2 to 1.
Right.
But you go like in a kind of cycle via some other state, then you may still have a thermalizing process in the sense of leaving the thermal state invariant. Yes, you can violate detailed balance. It would be nice to remove it.
I tell you that because we've been working about this kind of questions lately with Valerio Scarani also in US. And we came to the conclusion that very often this detailed balance is invoked when people need to construct a reverse process or to speak about reverse trajectories and then work out balance relations and so on. So in terms of reverse trajectories, you can also derive entropy production, you know, these kind of things. And it seems to us that the core argument there is just statistical retrodiction. So detailed balance is there just because formulas becomes easier, but you can typically do the same also for processes that do not satisfy the detailed balance if you construct the reverse process in terms of retrodiction, which is Bayesian inversion. So that's why I'm fixated with this aspect of your work, because
that sounds very interesting. Yeah, I mean, so I know that's a Crookes theorem, which is probably the kind of thing you were thinking about. That I think of it as kind of extending detailed balance to the case of including work. So taking detailed balance as a starting point, and then what happens to that expression of the ratios of the forwards of jumping up in energy to the ratio of jumping down in energy. What happens to that if you allow both for thermal transitions and work?
I see.
Then you basically get Crookes theorem. Yeah. So, but if you can get away from that, of course, it's nice. So, but I'm not sure if I understood how you think that you can. Like for what example that you can get away from it in the method.
Well, of course, it depends what you exactly need. But I will be thinking about these things on Thursday, so maybe if you have time.
Oh yeah, sure. Yeah, that sounds very interesting.
Okay, thank you very much.
Yeah, thank you.
So, is there any other question? Okay. If there is no, it's time. It's 1 o'clock in Japan and 12 o'clock in. Oh, sorry. Yes.
Yes. Thank you very much for the share.
Thank you very much for the talk. Thank you for the Professor Oscar.
Thank you.
Yeah. And yes.
Yeah. Okay. Well, so yes, thank you, everybody. I hope it was understandable. I guess there's a section of the quantum information community that has studied this topic before, like Professor Buscemi. But for the more mathematical people, maybe this information geometry thing is good. If you want to look in that direction, I think you might like that part. Yeah. Where is it?
Yeah.
Yeah. Okay. This information geometry thing. Okay. This one. Yeah. Okay. Yeah.
Shira is 19. Yes. And yes. Thank you very much.
Yeah. Okay. Thank you.
And do you have any announcement? Yeah, Professor.
Yes, I have already put the Remo link at the chat box. So please go to Remo if you have further discussions or some conversation. And the afternoon session will begin as the schedule. So see you again at 2 o'clock for China and 3 o'clock for Japan. So thank you very much.
Thank you.